I'm going to talk about the Arduino Due and the Pedal Shield, what these are, how they work together, and how they provide some exciting possibilities for digital signal processing and the nerd musician.
Awesome.
Okay, so first, what is the Pedal Shield? So the Pedal Shield comes shipped, looks like this. It's basically a circuit board and some components. This is something that you have to solder by hand to get it into a state where it can interact with the Arduino Due. I'm going to actually pass the assembled unit around. If you would, you can play with the knobs, but don't mess with this too much. It's a little on the delicate side. So basically, like I was saying, you have to solder these pieces together. It's supposed to take somebody who's decent at soldering about 2 hours, and it took me about 9. Okay, here's the Arduino. This is the microcontroller unit. So the pedal shield, once it's assembled, and the Arduino are connected together, kind of like in a sandwich, to produce a guitar Stompbox, basically. So one thing I wanted to point out: this isn't the standard Arduino Uno. It's an Arduino Due, which is more suited to signal processing, especially processing of sound. But like,
question? But I see there's 2 micro SD. Why are there 2? Is one for debugging?
Oh, you mean USB?
Yeah, these right here. The micro USB.
Yeah, those are USB.
Yeah.
Actually, I'm not sure why there's 2. I think it may be so you can power one with one port and send code to it with the other port. But I haven't found a use for 2 yet. That's a good question.
I was hoping you were going to say that one's for sending code and debugging, and the other one is just like a COM port.
Yeah, I'm not. That's a good question. I haven't got that far into it, but that might be the case. So.
I think it is for that chip.
So does the Uno only have one?
Yeah.
Okay. Who said that?
How many milliamps are you powering the board with?
I think, well, 500 normally, because I'm just plugging it out of my machine, but I think minimum is maybe like 300 or something.
Basically, the Due is
that's what it sounds like. I think
12 imports instead of 2. We have 2 USBs instead of 1.
Well, I think the big difference is the processor is a 32-bit processor, whereas the Uno is an 8-bit processor. I believe that's right. Let's see. So basically, the Arduino Due and the assembled pedal shield combine to become a guitar Stompbox. Does everybody have like a good idea of what a guitar Stompbox is? I think most people kind of do. Yeah. Okay. Basically, it's something you plug your guitar in and it changes the sound somehow.
Oh, that's distortion that we tried to get rid of.
Yeah, kind of. Actually, we're going to hear some of that later. So here's a diagram of kind of how the Arduino Due and the pedal shield work together. Basically, guitar signal goes in. The pedal shield prepares the signal to it actually brings the signal up to an appropriate level for the Arduino Due. See, everything in blue is Arduino, everything in green is the pedal shield. So it goes through analog to digital conversion inside the Due, gets processed through whatever algorithm we programmed for it. The signal then goes to analog conversion, and then back to the pedal shield. And then from the pedal shield, it goes to a guitar amplifier. I think what's interesting to note is pretty much the Due is doing most of the hard work. Everything in the digital domain is handled by the Arduino Due, as well as any kind of conversion from analog to digital and the other way around. Basically, the pedal shield's just making it easy for the Arduino Due to accept these kind of signals. So why would we bother with creating some of this digital signal processing ourselves? There's a lot of commercial products out there that do similar things. I think the advantage mainly is that the possibilities are endless. You can, if you think of some new kind of algorithm or process you want to put sound through, you can implement it. And if it's yeah, you can. It would just only be limited by the processing power of the Due. So if you came up with an effect that's, innovative enough, it could possibly even make you money. So I've been kind of into this technology for a while and researched a couple other similar products that allow you to program custom algorithms. And I even have another. I actually even bought another product a couple years ago, but I couldn't figure out how to use it. And that's a big difference between the Arduino Due and Pedal Shield combination and other products. The Arduino Due has a huge community around it, so it's really easy to find information about it. Once I got the unit assembled, I was able to, in maybe a few hours, get something up and running. Also, the hardware is really cheap, and it's really customizable. I think the hardware cost without shipping is only about $90, which is pretty cool for a unit like this. Most other similar things are a lot more expensive. And like Dan was saying earlier, this isn't necessarily Internet of Things because it doesn't connect to the internet, but it's really in the same vein. It's a microcontroller. You can buy add-ons to it, so it can connect to the internet. Another great thing about Arduino is the usability is pretty good. Setting up the environment, basically all you need is these two links. One is a driver, one is an IDE, and you can, with minimal configuration, you can get it up and running, sending code to the Due. It's really easy. Actually, I'm gonna show you the IDE. It's kind of like a cute IDE, I would say. It's pretty straightforward. It's not full-fledged at all. I wish I could, but I can't. I can't zoom in on the text because it's not a full-featured IDE. Oh wait, what's this? Maybe I can. Nope.
Be able to change the resolution on the monitor.
I could, but it's probably gonna mess up the streaming and stuff. But the great thing about it is it's pretty smooth setup. It already includes the libraries that you need to interact with the Due. Let's see.
If you hit the Windows button and the plus, does it make it bigger?
Let's see. Oh, magnify. That's nice. Okay. So here's some of my code.
C?
Yes. C.
C-like?
Good catch. I think it's technically a subset of C. All right. So coding for the Arduino Due, like Joe just caught, it's basically a C variant or a subset of C. I think probably most of us code in something that's a little higher level. Is that right? Anybody code at? Anybody doing anything in C? Okay. Okay. But I mean, it's even lower level than C#. It's not even object-oriented language. Crap. Sorry. I sure did.
Unplug it all the way and plug it back in.
Wonder how it's going to affect the video capture.
There's a repeater underneath the table. I can reset it if we have to.
Okay.
I think I do.
Okay. All right. Got it. Sorry about that. Again, this got reversed. Also, something else to keep in mind, in general, C is closer to the hardware, so you got to keep the hardware in mind when you're programming for it. And with a device such as this, you also have to keep specific hardware considerations in mind. You can get a lot more out of it if you understand the hardware. Now, I've only really scratched the surface, so I have a lot to learn, but what I have learned is that knowing the hardware is good. You might not know it yet too well. So I wanted to code something simple for demonstration for this presentation. And so what I coded for this pedal is a decimator. And so what that is a purposeful reduction in the quality of audio. So I talked to actually a couple other people about this project, and both people were like, why would you want to reduce the quality? Most of the time when we're talking about digital systems, especially audio, we want to get the best quality possible. So to answer that question, hopefully I'll be able to demonstrate some of the interesting sounds you can get from this process. But really, if you recognize the sound, you might actually hear it in a variety of different musical styles, especially electronic music, of course, but also pop and rock. There's like a certain nostalgia to the sound because we're reducing the quality, so it might sound like some older devices. It's kind of a harsher sound if that fits your aesthetic, and it just can add some variety and interest. So to try to explain what I'm going to do with this pedal, I first have to go back and describe some digital audio concepts. This is an analog sine wave. It's about 2 milliseconds of a sine wave at the frequency of 1 kilohertz. And let me demonstrate what that sounds like. So, pretty straightforward, clean sound.
How did you generate that sound? I mean, on your phone the first time, did you download a wave file or? Actually,
there's a sine wave generator, or signal generator I found.
Sweet.
Yeah. So, let's see. So just to explain this graph a little, the horizontal axis is time, the vertical axis is amplitude, and you can see it varies over time. Digital systems can't represent analog data directly. The only thing you can really do is approximate. So here's one way a digital system could represent an analog signal. Basically, there's data points taken at time intervals. So each red dot in this graph is represented by a 16-bit number. So I think it's pretty natural to us to understand integers and stuff that the more bits that represent each of those data points, the closer to the analog signal we're going to get. or actually the more accurately we're going to reproduce that analog signal. So here's the data points where each point is represented by about an 8-bit number. You can see how the dots are starting to get less accurate. And here's a 3-bit number. You can see they're way off. And also another thing I wanted to mention is that this scheme of encoding analog data digitally is known as pulse code modulation. It's not the only way to represent analog digitally, but it's probably by far the most common. So just to reiterate, the bit depth or bit resolution of each data point is an important measure of digital quality. So I'm going to demonstrate what happens when we have that data represented by fewer bits. So I'm going to, you probably can't see, but as I turn this dial, the data is actually going to be represented by fewer and fewer bits. Sorry if that's enough. Shoot. Actually, you know what? Sorry if that's annoying. So I think I'm going to need to recompile this code. I think there was an issue. Yeah, so oh, I know what's wrong. Okay. Red. This will give us a chance to see the compilation process, I guess. Okay. Okay, so here we go. So as I turn this dial, it's going to be represented by less and less bits. You can hear the sound changing a little bit. Now, at one point, it can't even represent the sound at all. Okay.
So like for a CD or something like that, what's the sampling on that?
That's a great question. I was going to mention that, but a CD is represented by 16-bit numbers. Yeah, I was going to wait to mention that when we were talking about free sampling rate, but that's right, yeah. And that's
the same rate as the Duo with 16-bit sampling?
Sort of. There's actually two 12-bit converters. They can be combined to get something like 24-bit resolution. Though I haven't fully understood how they're combined yet, but 12-bit does a pretty good job. So that was just a kind of the scientific signal or something that we're using. So let's demonstrate what it sounds like when we're playing an actual instrument. So let's play a riff with virtually no processing. So let's add some significant processing to it and see what happens. And let's loop that so we can vary it a little bit. You hear it getting more intense? So, so that's, sorry. So that's actually one of two sections of the effects processing of this pedal. Is reduction in the bit depth of the audio that it produces. Another important measure of quality was kind of already mentioned before, the sampling rate. And that's basically, if you look at this graph, is how far apart each of these data points are. So it's measured by how many times per second that basically the digital system goes out and looks at the analog signal. So basically, the higher the sampling rate, or the closer these dots are together, the better the signal reproduction is going to be. There's this other important concept when we're talking about sampling rate, and that's the Nyquist frequency. Basically, to define that, it's 1/2 of the sampling rate. For example, say the sampling rate is 2 kilohertz, or 2,000 times a second. The highest frequency our system can reproduce will be 1,000 times per second, or 1 kilohertz. Like we were saying before, CD quality sound is 44.1 kilohertz, which makes the Nyquist frequency of it about 22 kilohertz, which is near the upper limit of frequencies that a human can hear. That's why the system was given that sample rate. Okay, so what happens if we try to insert an analog signal into a digital system and it's above that Nyquist frequency? Well, the frequencies don't just go away, they don't get filtered out, they actually are reproduced inaccurately by the system. So if you look at this diagram, this blue line again represents an analog signal, and the red dots represent our digital data points. Now when this signal gets converted back to analog before you hear it, it's actually going to reproduce a different frequency completely than the input signal. And I'm able to demonstrate that again with the sine wave. So I'm actually reducing the sample rate gradually. You can hear at a certain point,
It's a different frequency.
there's a whole different sound. And as I decrease the sampling rate, that pitch actually goes down. So again, to demonstrate this through through an actual instrument sound. See, at one point the sound gets kind of weird.
Yeah, that's cool.
Yeah. And the cool thing is you can actually combine these two different kinds of decimation together to get different effects. So now I'm going to add the bit depth reduction. And you can see how I can play with the dials and kind of goof around and get cool sounds. Also, let me demonstrate how another sound sounds through this effect. So this is a pretty clean drum sound. Add some bit resolution reduction. And then some sampling rate reduction. So you can get some interesting sounds from it. So this is pretty much the device I worked on for this presentation. there's a lot of other applications for digital signal processing beyond audio. Image and video processing is included. Basically any data that varies over time or over some other kind of independent variable can be processed using digital signal processing. So it's applicable to medical applications. I gotta think big data and logistics are included because it's data that varies over time.
So what would you do? You'd filter out certain things?
Yeah, I would think it would be useful for saying frequencies. I don't really know how it would be applied, but with all the work that's been done on signal processing, I gotta think there's something that would be useful.
What kind of medical app could you do?
I probably yeah, that's good. I was just thinking maybe something with heartbeat monitoring, measuring frequencies with heartbeat monitoring.
I think that'd be cool.
Yeah.
I thought about building something to measure my sleep at night, figure out why I'm not sleeping well every night.
Yeah.
I mean, Intellitrix uses sampling.
The what?
Intellitrix uses sampling when it comes to metrics on how fast the methods are taking. It's literally sampling everything running and just taking samples of time and then using that to extrapolate what the actual time is for the actual application. Redgate also does the same thing. You can either do sampling or you can do like a full board or go, burn down your house with your CPU on fire. Full sampling. It gets hot. But yeah, most of the code coverage tools and the time profilers do sampling by default because it's so intensive to capture all that data.
Oh, I see. So you don't get the data at all points. You
Right.
sample it.
So what
Okay.
they're saying
You get like a
is,
snapshot.
We're going to sample it for a couple seconds and not sample it and sample or throw away every third call if you're not the, like there's all kinds of ways you can tweak like Redgate and, I've also written a timing profiler, but I sample everything, but then, again, that CPU just starts ripping away.
Yeah. Interesting.
Especially trying to create, capture all the calls and all the tail calls and capture the entrance and the exits. There's a lot of ways you can get out of the method. It's
Okay.
being in front of them. There's no true, normally you hit a no op and then you exit, but if you throw an exception, then your stack trace goes to hell.
Right.
So the sampling is supposed to eliminate most of that. Like we try to say, look, this is kind of where it's at, but if you truly want to track down a bug and you truly want to find out where it is, take a long time, you need to let the application just shred your CPU and run it.
Gotcha. Okay. Interesting. I know DSP digital signal processing. I believe it's part of an engineering curriculum. Is that right, Dan?
Yeah,
So it's really important to engineering. Yeah. Okay. Actually, in my research, I found this article where this guy who was developing some kind of signal processing algorithm to analyze big oil data. He was an engineer for like oil. He actually was the guy who invented auto-tune. Do you guys know what auto-tune is? Okay.
Yeah.
So. Really?
Oh my God.
Okay. Anyway.
There you go.
Yeah. Yeah. But.
Look up Richard Feynman auto-tune.
Or is it like auto-tune the news where they take like the daily news and like auto-tune?
Well, that would be impossible without
Yeah.
without that. Yeah. They do? I was looking for one. Nice. Okay. Yeah. Yeah.
Sweet.
Okay.
It blows my mind how fast they can figure out the data.
So that's about all I have. I have some references up here. The top one is my GitHub project for the Arduino Due code, and then just some other miscellaneous things that might be useful. So thanks. Does anybody have any questions?
I want you to look at a network shield on it, so while you're playing, people can change.
Oh yeah, that'd be cool.
You don't even
That'd be
need
cool.
the analog
Yeah, actually.
controls, right? Because then you're digitally changing.
Right.
the code.
Exactly. And I wanted to get into some controlling of it, from an external source, but I didn't have time. That's a cool idea.
You can probably do that with the USB.
Where are you
Yeah,
saving
I'm
the
thinking.
sampling? Is it in RAM or is it an SD card on that? Or
The samples aren't actually stored; they're processed immediately. You can store them in memory, to whatever limit is on here, which I didn't even get into that too much because I didn't need to, because I was basically processing them in place and then sending them right out.
Or were you talking about the loop?
yeah, I was wondering. If
Yeah, that's a different processor is giving me the looping effects. Yeah, that was just for demonstration purposes.
Okay.
Yeah, sorry to disappoint you.
So what did the floor pedal actually store, like 3 samples of 3 seconds of sound and then just loop it?
Yeah, basically. Yeah.
I didn't even see that. There.
Yeah, this is a commercial processor. It does a bunch of really cool things, but yeah. So.
So you're gonna try to make some new effects too?
Yeah, I'd like to do some more work on this to make it usable maybe in a live performance situation, and I have some other ideas for some vocoding effects, if you know what a vocoder is. It's where you combine like a synthesizer sound and a vocal sound, or a drum sound and a vocal sound.
Digital Peter Frampton.
Exactly. That's a great way to put it. Yeah.
You know who Peter Frampton
Don't ask me a question.
So.
So he's not there on either side, Peter Frampton or somewhere in the middle, right? Smashing Pumpkins, maybe?
Okay.
So.
Awesome. Thank you, Andrew.
Yep. Thank you guys.